Last time, we talked a lot about the idea, I didn't mention the name, but here's some jargon for you. We talked about the idea of deleting dominated strategies. Looking at a game, figuring out which strategies are dominated, deleting them, looking at the game again, looking at which strategies are now dominated, deleting those, and so on and so forth. And this process is called the iterative deletion of dominated strategies. This is not a great title for Barry's book. You need to do better than that to get the $250, right? This is a boring title, but never mind. Iterative deletion of dominated strategies. The idea, it embodies the idea of putting yourself in someone else's shoes and trying to figure out what they're going to do, and then think about them putting themselves in your shoes, figuring out what you're going to do, and so on and so forth. And last time, we saw already that this is a very powerful idea, all right, in that game last time, but we also saw it's a dangerous idea to take too literally, that sometimes this can get you to overthink the problem, and actually, as in that numbers game last time, the the best choice, the winning choice, might not involve so many rounds. All right, we also saw in that numbers game last time that in some games, but by no means all games, in some games, this process actually converges to a single choice. In that numbers game, it converged to 1. All right, so just to say once again what this idea is you yourself should not play a dominated strategy. Delete those for everyone else. Whereas everyone else is not going to play a dominated strategy. Delete those. Look at the game with all those dominated strategies deleted. See if there are any strategies that are now dominated. Delete those. Look again, etc., etc. All right, I could write that all up. We saw it in practice last time. It's probably just easy to have the idea there. All right. One tip about this. Try to identify all the dominated strategies of all players before you delete. Then delete, then look again, try to identify all the dominated strategies of all players again, and then delete. That process will prevent you from getting into trouble. All right, so today I want to be a little bit less abstract, if you like, and I want to look at an application. I want to look at a famous application from politics. All right, so we're going to look at a model of politics. All right, and the idea is going to be this. We're going to imagine that there are two candidates, and what these candidates are doing is they're choosing their political positions for an election. So that these are the players, and the strategies are going to be, they're going to choose positions on a spectrum, on a political spectrum. And to make life easy, we're going to assume that this political spectrum has 10 positions. So here are the positions. We'll call them 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. All right, not very difficult. All right, what's the idea here? We haven't finished describing the game. What's the idea? The idea is that these positions are left-wing positions, and these positions are right-wing positions. Can people not see past the podium? Let's get it out of the way. All right. So you could think of these extreme left-wing positions. These are people who, I guess, they don't eat anything except for fruit, and they think the trees should have the vote. All right, and these guys out here, these are the extreme right-wing positions, so they think, they think the poor shouldn't have the vote, and they eat immigrants. All right? I'm an immigrant, I'll be careful. The candidates here are going to try and choose positions. We're going to assume, this is not realistic, we're going to assume for now that there are 10% of the voters at each of these positions. All right? So there's 10% of the voters at each position. So they're uniformly distributed. All right? And we're going to assume that voters will eventually vote for the closest candidate. All right? So voters vote for the closest candidate, or the candidate whose position is closest to their own. And we'll need a tie-breaking assumption, and we'll do the obvious tie-break. If there's a tie, then the voters split. The voters of that position split evenly. All right, so if there's a tie, half the voters at that position go for one of the candidates, and half of them go for the other. All right, so here's a game. I've got the players, that's the candidates. I've got the strategies, that's the political positions. What am I missing? I'm missing payoffs, right? I'm missing payoffs. And it matters in this game a lot how we specify the payoffs, but we're going to assume that the payoffs are that the candidates aim to maximize their share of the vote. Right? Now that's not the only thing we could have assumed. We could have assumed that all they really care about is winning, and that winning gave them a high payoff and that losing gave them nothing. Right? I'm going to assume a little bit more. I'm going to assume that they haven't spelled maximize right. Max will do. Right? They want to max their share of the vote. Right? The reason this isn't a terrible assumption is you could think that getting a higher share of the vote gives you a mandate, or if this is a primary election, you want, a larger share of the vote gives you a bigger push for the next primary or whatever. All right, so we're going to assume that they're trying to maximize their share of the vote. All right, so we want to know what's going to happen in this game. It seems like a pretty natural, pretty important game. Okay, so given what we've learned so far in the class, a natural first question to ask is, are any of the strategies here, there are 10 strategies, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, are any of the strategies dominated? Are any strategies dominated? Let's get some, let me get my microphones up and ready a little bit. So any strategies dominated? How about this gentleman in blue? So stand up and shout, yeah.
Okay, 1 and 10 are both dominated.
All right, so this gentleman whose name is?
Stephen.
Stephen says 1 and 10. We'll come back to 10, but you're right, we'll come back to 10. So he says that position 1, strategy 1, choosing the most extreme left-wing position is a dominated strategy. What dominates it, by the way? Stephen, want to shout out? 2. So for example, our conjecture here is that 2 dominates 1. 2 dominates 1. That's the claim. Right? And let's just be careful here. What does it mean to say that 2 dominates 1? It means that choosing position 2 always gives me a higher share of the vote than choosing position 1, no matter where the other candidate positions herself. Right? It does not mean 2 beats 1. Right? All right. So let's take Stephen's conjecture and see if it's true. All right. All right. So in particular, let's start working out what share of the votes you'd get if you chose position 1 or position 2 against different positions the other guy can choose. All right. Okay. So for example, what we're going to do is we're going to test, does 2 dominate 1? And while we're doing this, we'll figure out how these payoffs work as well. All right. Well, how about versus 1? Right. So suppose the other candidate has chosen position 1. All right. So the other candidate has chosen position 1. Then we're going to compare my payoff from choosing 1 against the other candidate's payoff from choosing 1. We're going to compare this with my payoff from choosing 2 against the other candidate choosing 1. All right, let's figure out what that is. So what's my, somebody can shout this out, what's my share of the vote if I choose 1 and the other candidate chooses 1? 50%, that was pretty easy, right? Must be a tie for everybody. So I'll get 50% of the vote. And what's my share of the vote if I choose 2 and the other candidate chooses 1? 90%, right? In fact, he will get, or she will get, all the voters at 1, I'll get everyone else, so I get 90%. So in this case, choosing 2 is better than choosing 1. But of course, we're not done yet. We have to consider other possible positions of my opponent. So suppose my opponent chooses 2. So now we're comparing my choosing 1 when my opponent chooses 2, and the payoff I would get if I choose 2 when my opponent chooses 2. Okay? So what's my payoff if I choose 1 and my opponent chooses 2? I get all the voters right on top of me at position 1, and she gets everyone else. Is that right? So I get 10%. And what about if we both choose 2? 50%, everyone happy with that? All right, so 50% in this case. And once again, 2 did better than 1. Everyone happy with that? So we showed this choice was better and this choice was better, and we're going to keep on going. Against 3. So now we're comparing my choosing 1 versus 3, and my choosing 2 versus 3. If I choose 1 against 3, what share of the vote do I get? I'm going to get all the people at position 1 and half the people at position 2 for a total of 15. And if I choose 2 against 3, what do I get? I get 20. I get all the people at 1 and I get all the people at 2, so I get 20%. So we're okay again. Let's do one more just to see a pattern here. So if I choose 1 against 4, and comparing my choosing 2 against 4, in the former case, if I choose 1 against 4, how many votes do I get? I get all the people at 1 and all the people at 2, right? So I get 20% of the votes. She gets everyone else. And here, if I choose 2 against 4, I get all the people at 1, all the people at 2, and what? Half the people at 3. All right, so that comes out as 25%. And once again, and so on. Now, I could go on right the way through here, but I'm going to stop because it gets a bit boring after a while, right? Because I'm guessing you can see a pattern emerging here. What's the pattern here? What's the pattern here? Somebody? Raise their hand. Somebody raise their hand so I can get a mic out there. Can we get a mic in this guy in white? Stand up, stand up. Yep. Stand up, stand up. Stand up and shout.
2 is always better than 1.
2 is always better than 1, but we can see more than that, the pattern. That's right, but what's the pattern here? Get mic back in?
Whatever's closer to 5 is better than what's ever farther away from 5.
That's not quite the pattern I'm looking for. Let's look at the numbers here. We had 15, 20, then this went up to 20, 25, and so on. All right, so what's the pattern here? Yes, Stephen again here.
If your opponent doesn't choose 1 or 2, then you're always going to be 5% better off if you choose 2 than 1.
Exactly. So ignoring these first 2 positions are a bit weird. Choosing 2 always gave me 5% more votes than choosing 1, right? Regardless of what the other person chooses. So I mean, if you want, you can fill in the next, whatever it is, the next 6 positions and see, but you'll see that very clearly that Stephen's right, that choosing 2 will always get me 5% more of the votes than choosing 1 from here on down, and in fact they'll go up in intervals of 5. So in fact it is true, it is in fact true, so we can conclude that 2 dominates. In fact, we can do a bit better than that. We can say strictly dominates 1. Right? 2 strictly dominates 1. All right. Is anything else dominated here? Oh, Stephen already told us that 10 is dominated. I'm not going to go through that argument. Can everyone see that symmetric? Hang on a second. Can everyone see that 10 is going to be dominated by 9 in exactly the same way? Yeah, is that obvious? It's just really the same argument coming the other direction. All right, so similarly, 9 strictly dominates 10. All right, and again, we're not saying choosing 2 beats choosing 1, right? 2 wins against 1, or 9 wins against 10, right? We're saying choosing 2 always does better than choosing 1, regardless of what the other person chooses. And choosing 9 always is better than choosing 10, regardless of what the other person chooses. All right, there was a question. Are we okay? You want to get the mic in for the question? Yep, stand. Shout out to everyone.
I think you may have defined it already, but I couldn't find a definition of strictly in the book we have.
Ah, okay. Well, you have one on the handout. So I think there probably is one in there somewhere, but just in case, there's one. We've had 2 in class. There's one on the handout. Okay, good. All right. So we've concluded that 1 is dominated by 2 and 10 is dominated by 9. Is anything else dominated here? Well, what about thinking about whether 2 is dominated by 3. After all, I've forgotten your name, but that, what's your name there? Yes? Sudipta had suggested earlier on you want to be close to 5, so 3 is closer to 5 than 2. Is 2 dominated by 3? Anyone else? Any other hands? There's a hand here. Can I get this lady here?
Well, once you delete the dominated strategies, then you kind of go through it again, and then 2 is dominated by 3.
All right, good. So you're getting ahead of us. Good. So we'll get there. Hold that thought. Hold that thought. But what about right now before we delete anything? Let's check it out. Let's check it out. So in particular, let's just try this process. So how about my payoff versus 1, for example? So 2 against 1 gives me 90% of the votes. 3 against 1 gives me what? 85% of the votes. Which is actually lower, right? It's lower. So it's clear that 3 doesn't dominate 2. Right? 3 doesn't dominate 2. In particular, if the other candidate were to choose position 1, I would get a higher share of the vote choosing 2 than I would have done if I'd chosen 3. All right? So in fact, it's not the case that 2 is dominated by 3. But the woman whose name I either didn't get or forgot. Christine. So Christine has pointed something else. So Christine, when you wait for the mic and point that out again. Right, so we know that 2 is not dominated, in particular not dominated by 3, but, what's the but?
When you delete the dominated strategy of 2 dominating 1, or 1 being dominated, when you delete that and 10, then it is.
All right, so what Christine is arguing is even though it's the case that 2 is not a dominated strategy, if we do the process of iterative deletion of dominated strategies and we delete the dominated strategies, then maybe we should look again and see if it's dominated now. Right? So let's be careful here. We're not saying that we're going to delete the voters at 1 or delete the voters at 10, though we might wish to. Right? We're just saying all we're saying is we know that the candidates aren't going to position themselves at 1 and aren't going to position themselves at 10. So in some sense, we're deleting those strategies. The voters are still there. All right? All right, so let's try that. So if we... There's a but here, I guess. But if we delete the strategies 1 and 10, which were dominated, then does 3 dominate 2? And once again, we can try it out. All right, so let's try it out. All right, so the payoff from choosing 1, let's start against 2. So the payoff from choosing 2 against 2 is 50%. The payoff from choosing 3 against 2 is what? What's the payoff from choosing 3? Someone can shout out. What's the payoff from choosing 3 against 2? 80%, right? The person at 2 is going to get all the ones at 1 and all the ones at 2, and 3 will get everything else. So this is 80%. All right? Versus 3, the payoff of 2 against 3 is all the people at 1, all the people at 2, so it's 20%. The payoff from choosing 3 against 3 is, of course, 50%. So far, so good. So far, choosing 3 is better. Against 4, the payoff from choosing 2 against 4 is what? What's the payoff from choosing 2 against 4? Again, all the people at 1, all the people at 2, and half the people at 3, so that's 25%. The payoff from choosing 3 against 4 is going to be all the people at 1, all the people at 2, and all the people at 3, for a total of 30%, which again is bigger. Now let's do one more. Versus 5, the payoff from choosing 2, I can afford to raise this a bit, against 5 is all the people at 1, all the people at 2, and all the people at 3, 30%, whereas the payoff from choosing 3 against 5 is all the people at 1, all the people at 2, all the people at 3, and half the people at 4. 35%. And again, you can see exactly the same pattern is going to emerge here. From here on down, if I bothered to do it, we'd find that choosing 3 always gets me 5% more of the vote than I would have had from choosing 2 against any of these higher numbers. Right, the same pattern Stephen pointed out before. So, I've forgotten your name again, I'm sorry. So Christine is correct in saying that once we delete the strategies 1 and 10, once we realize that those positions are not going to be chosen by our sophisticated candidates, then we realize that probably choosing 2 and, of course, 9 isn't a good idea either. All right? So 2 and 9 are not dominated, but they are dominated once we realize 1 and 10 won't be played, or won't be chosen. All right? Okay, so where are we going here? Where are we going? Where is this discussion going to end up? Let's come back to our original game. All right? We've argued that 1 and 10 shouldn't be chosen because they're dominated. We've argued that once we realize those aren't going to be played, that 2 and 9 aren't going to be played. What's going to end up being played? Well, let's just go slower. So we were able to dominate 1 and 10 in the first round, so we know this won't be played, and we know this won't be played. Remember, the voters are still there, we're just deleting the strategies. Then we dominated, then we ruled out, I'll put double crosses for in the second round, 2 and 9. And then we ruled out 3 and 8. And then we ruled out, we would have done 4 and 7, and that leaves just 5 and 6. All right? So if we do the procedure of iteratively deleting dominated strategies, going back again, looking at what's dominated, doing it again, all that's left is 5 and 6. So this procedure leads us to conclude that the candidates will choose positions 5 and 6. Does 5 dominate 6 or 6 dominate 5 or anything like that? No, at that point it's just a tie, right? So at the end, the procedure, so iterative deletion, it's called itdel, leads to deleting all except 5 and 6. 5 and 6. All right. So this was just a simple exercise. I'm hoping that was a simple exercise. Let me just look out there. Everyone following that okay? That really wasn't meant to be hard. All right. But what's relevant about this exercise is not the fact it's hard. In fact, it isn't hard. What's relevant is the fact it's relevant. All right. It's about the real world. All right. In particular, this is a famous model in political science. Does anyone know the name of this model? What's the prediction here? The prediction here is that the candidates are going to be squeezed towards the middle. They're going to choose positions very close to each other and very close to the center. What's that called? Anyone know? Sorry? Hold the thought on that. Hold on that. Someone at the back? Shut. This is the median voter theorem. Thank you. Thank you. Let's have a new board. This one will do fine. So the prediction is candidates crowd the center, and this is called, in political science, the median voter theorem. It's called the median voter theorem because the voters at the center, in this case 5 and 6, actually get to decide not just the election, but decide, therefore, what policies are put in place. All right? How does this do as a prediction of the real world? All right, how does this do as a prediction of the real world? Well, there are examples in American history in which the median voter theorem looks pretty good. They're pretty old examples. They're going to be before you guys were born, but let me mention them anyway. So I think a lot of people, if you go back today and you look at tapes of the Kennedy-Nixon election in 1960, some American help me out here, 60, right? right? I think of 60. So in the 1960 election between Kennedy and Nixon, if you go back and look at those tapes, it's amazing how conservative Kennedy looks when you think about his reputation today. Right? They really were crowding the center. And 8 years later, Nixon seemed to have learned his lesson. So if you look at the 68 election, which Nixon won, Nixon sounds on those tapes, because his policies being put forward in that election, he looks extremely liberal for a Republican. All right? So again, they were crowding that center space. Some people argue that that's exactly what Clinton did in '92. He took the Democratic Party to the right, i.e. towards the center, in order to pick up those central voters and win. So there are examples in American history of elections that in which the median voter theorem seems to do well. All right? And we'll come back and discuss it more in a second, but before I do, let me mention that the same model, exactly the same idea, has an application in economics. Somebody mentioned it already over there. All right? The application in economics is to do with product placement, the thing that Jake's working on. All right? In product placement, you might think, let's think you're placing a gas station. You might think it would be nice if gas stations spread themselves evenly out over the town or out over the road, so that whenever you happen to be, when you ran out of gas, there was a gas station close by. That would be convenient. But unfortunately, gas stations, as we all know, they tend to crowd into the same corners. They tend to be on the same road junctions, right? Why? Because they're competing for voters who happen to be close or running out of gas at those moments, and by crowding together, they avoid being outcompeted by each other in terms of position. I said that a bit quickly, but we'll come back and look at that idea in more detail later on in the class. All right? All right? So in politics, this is about candidates crowding close together towards the center to try and get as many voters who are close to them. And in economics, this is about firms crowding together to try and get shoppers who are close to them. All right? And the people associated with this are a guy called Anthony Downs, who did this in political science in a book in 1957, and in economics, a guy called Hotelling, who wrote a paper about this in 1929. And in political science, they call this simultaneous discovery. I think 1929 is a bit earlier, but never mind. All right. Now, what I want to do now, and I want to do this periodically in the class, we have a model up there, and we've got to analyze it. We've used a bit of game theory to analyze it. I want us to talk about whether we think it's right. What do we think of the strengths and weaknesses of this model? All right? So what I want you to start thinking about is, do you believe this model? Is this a good model of politics? What's it missing? All right, let me come off the stage a second and try to encourage you to get involved in the discussion. How many of you are poli-sci majors? Now, raise your hands if you're poli-sci majors. A bit more. A lot of you. By the way, how many of you poli-sci majors have seen this model before? Some of you have seen it before. All right. So what's this model missing? And you all live in America. You all live in a democracy. I mean, you don't all live in America. A lot of you live in a democracy. So you have some idea about this. So what are we missing here? So can we get the woman here, Ali? Yeah.
Voters are not evenly distributed. 10%, 10%, 10%.
All right. So one thing that seems odd about the way we set up this model is that the voters are not evenly distributed. Let me go and put that up, and I'll be a bit. It'll be tiring, but let me go to and fro a bit. All right. So one thing, what's missing, or wrong, if you like. Well, one thing is the voters are not evenly distributed in the real world. Okay? Good. Anything else? Good. We'll talk about each of these in turn. Can I get the guy over here? Sorry, I'm not making this easy for Jude. Let me just stay down here. I'll collect up a few and then go back to the board.
The model doesn't take into account differences between the groups in voter turnout based on the candidates?
Good. So there's an issue of turnout. Right? We assumed here that everyone votes. Is that right? But in fact, not everyone votes. There's always the option of not voting. All right? Well, remind me to put that one up. That's okay. Not voting. I have to remind me of these. Okay. How about the gentleman here in yellow?
There's a difference between the primary and general election.
Good, good. So we assumed, we kind of jumped to just one election, and at least in the American system, for better or for worse, I could voice an opinion on that, there are lots of little elections on the way. There are primaries in all these states that you probably have heard of. States you probably have heard of on the way. All right, anything else? Anything else? Can we get where's the other mic? Can we get the woman in green here?
American voters often vote based on character rather than position.
All right, so there's more than just position. So another way of saying that, so stop me if this is wrong, but one way to say that, we've been assuming that politics is one-dimensional, left, right, and there might be other things involved, character, or even among issues, even among political issues, it could be more than one dimension. It could be that there's a dimension about the environment, and a dimension about foreign policy, and maybe another dimension about redistributive politics. All right, so that's an important idea. Let me get a couple more. Can we get...
The model might not apply with more than 2 candidates.
Good, good. So another issue here is, I just assumed that there were 2 candidates. All right, we know in some elections there was a 3rd candidate. For example, there was Nader in the election in, and, well, I guess he was there in the other one as well, but he was particularly there in 2000. So by the way, I don't mean this as a joke. In some sense, there's always a 3rd candidate, and that comes from the point we had earlier, because not voting is always an option. All right? So in principle, in that election in 2000, there was at least 4 candidates, as it were, 4 things you could do with your vote. You could vote for, as it was in that time, Gore, Bush, Nader, or not voting, and I'll leave it to you to decide which of those is equivalent to not voting. Anyone else? Anyone else? There's one other thing I think was really, maybe some small things, but one other really glaring thing here. One other glaring thing. It's one I haven't had yet. Ali, help me out here. So, let me get this guy here.
Extrapolating from the fact that there are different things which people take into account, not everyone closest to 6 might actually vote for 6. They might be curve inserts.
That's true, although that may be a question of dimension. I had a different thing in mind. Let me say it, all right? So I think this is important. A candidate could say during an election that I'm a moderate candidate, I'm at position 5, but you might not believe him or her, right? You've got the candidate's track record. Unless that candidate can commit to policies at position 5, you might know full well that the candidate is in fact a position 10 or a position 1 candidate. Is that right? Is that right? So unless the candidate can actually commit to a position, all right, there may be a problem in them simply announcing my position is moderate. So again, let's think of an example here, a couple of examples. In the Bush-Gore election, we saw President Bush, well, candidate Bush as was, saying, I'm not a right-wing candidate, I'm a compassionate conservative, and you guys believed him. No, I don't know, maybe he was, I don't know. His track record in Texas probably did actually look a lot like that. Or today, if you look at both primaries going on now, you're seeing various candidates on both the Republican side and the Democratic side seek to position themselves. But as you all know, those candidates almost all have track records, and not everybody believes that Hillary Clinton is quite so centrist as she now seems, and not everyone believes that the former governor of Massachusetts is quite so conservative as he now seems, right? So it's not clear that you can just choose your position willy-nilly. All right? So let's put some of these up. All right, so I'm going to forget them, so you have to help me out a bit. So we have many candidates. We have many candidates, more than just 2, or we have not voting, which is related to that, actually. And we have choosing your position, the inability to commit to a position. All right, so your position may be not believed. And I want to claim that that's connected to the idea that you can't commit yourself to your policies. And we had some others. We had primaries. And we had other dimensions. So we had high dimensions. Have I got the main ones now? I think I got most of the main ones. So there's lots of things, when we look at this model, there's lots of things that are missing. A lot of things are not seeming to be captured by it. And here's where I want to get a little bit more religious, if you like. It's tempting to say, look, we read out this model, it's missing all this stuff, so it must be useless. It's just, you know, we shouldn't model it. You might even go further. You might say, modeling, you're always going to miss stuff out, so let's just not bother. And that, I think, is the wrong conclusion here. The right conclusion, I think, is the reason we write down these models is to try and capture and test our intuitions. In this case, the intuition about crowding towards the center to get votes. But of course, these models abstract from very important parts of reality. And the next step to do is what? Is to say, okay, now let's try to enrich the model, to add more into the model, and see if you get a different result, and if so, why? Right? So you start with your basic model, then you add in, you enrich the model, and you see if the results change, and that'll help you explain why you're getting different results in different settings. All right? So the sort of religious part of today's class is models are always abstractions. You want to use them to see what's missing and then add things back in to see if they make a difference, and if so, how. And let's go through these a little bit. So it turns out that the very first one, voters are not evenly distributed, is certainly true. It's undoubtedly true, but it turns out that if you make the voters distributed more realistically, let's say in a kind of bell curve shape, it makes actually no difference to the result at all. All right? So this is true, but it doesn't actually change the result. So this one we're okay. Whoops, the result survives this change. All right? What about the one about many candidates? Well, clearly that matters a lot, right? We know that there were many candidates in the 92 election and the 2000 election, and we know that not voting is important. So this one I'm going to let you see whether it makes a difference. This one's going to be on the problem set. All right? So I'm actually going to get you to do this. Let's go back to the model, add an extra candidate, and see what happens. Right? You can learn whether it makes a difference. I'm not going to give it away. The one about committing to policy. This is important. It's really hard for candidates to convince you that they really are a left or a right or a centrist candidate. Let me give a historical example outside of America, but in the real world, in England, in the 97, in the 80s and 90s, the Labour Party in England had lost election after election after election. And in each election, it would come forward and say, we are not really a left-wing party, we're a centrist party these days, and people would say, we don't believe you. All right? So what Tony Blair, the guy who won the 97 election, did with New Labour policy was he managed to commit to a centrist policy by literally committing to it. He took in England you have to publish your economic and financial plans of the government 5 years ahead. So he took the financial plans of the Conservative government that was then in power 5 years ahead, and he said, these are my financial plans. I'm going to announce these today as my financial plans 5 years ahead. They're exactly the same policies as the Conservative government has. So not only was he choosing a position close to the Conservatives, he was choosing exactly their position. And it came down to what somebody else said here. That left the election on the other dimension, which might have been character or whatever. All right? And that won by a big way. All right? So nevertheless, even having given you that historical example, we're going to come back and we'll look later on in the class at a model in which politicians cannot choose their positions, but rather you know their positions ahead of time. So we'll do this one. We'll do this one later. Right? And these other two, primaries and higher dimensions, they're both great points. We're not going to have time to do them in this course, but if you take a class in the political science department on voting and on elections, on modelling elections, you will see that both of these have been modelled and discussed in great detail. There's even some empirical work on just how high dimensions are really involved in elections. All right? So this is great stuff for this area of political science. All right, so I want to inspire you to take some more advanced courses, albeit in another department. All right, so have I convinced you that there's at least something you can do with iterative deletion? We used iterative deletion in a relatively abstract setting, or not abstractly, but a play setting last time, in which we was choosing numbers. And then we talked about it in terms of Hannibal invading Rome, and now we've seen how it applies here in an election game, and I think that's probably enough for iterative deletion. So what I want to do now is I want to switch course and introduce a new tool. This is what we'll do typically in the class. We'll have new tools, we'll see how they apply, we see what we can learn with them, then we'll move on to a new tool. All right? So I'm going to switch to a new tool. Any questions at this point? Everyone happy at this point? Well, happy is too strong. Are people satisfied at this point? All right, okay. All right, so we're going to move away from this example, and I'm going to introduce a new subject. I'll need several boards, I think. So let's collect them. All right, so that little semi-religious speech about modeling, I think economists, those of you who are economics majors, you're thinking, yeah, what's the problem? For those of you who are history majors or political science majors, that's more of an issue, right? So you really want to think about why we're modeling, what do we get for this exercise? All right, I want to move to a different approach now, and the different approach to analyzing games is going to be about what we're going to call best response. And to kick this off, let's look at an example. So here's a game, very simple game with two players. Player 1 is choosing up, middle, or down, and player 2 is choosing left or right. And the payoffs are like as follows. They're nothing very interesting. They're just some numbers thought up for the purpose. 4, 2, and 2, 3. So they're 5, 1, 0, 2, 1, 3, 4, 1, 4, 2, and 2, 3. All right. So first of all, let's try and analyze this game using the tools we've learned so far. So does either player have a dominated strategy? Take this. So I claim that neither player has a dominated strategy. Let's just check. So for example, you might think down is dominated. You might think down is dominated. But if we look carefully, we see that down actually does better than up against right, and down does better than middle against left. Right? And similarly, we can see that right is not dominated because it does better against up than does left, but left isn't dominated because it does better against middle than does right. Right, and so on and so forth. So you can work through this game and you can check pretty quickly that nothing is dominated. So if the only tool I taught you in this class was dominated strategies and the iterative deletion of dominated strategies, we'd be stuck. Right? Wouldn't be able to get started on this game. Nevertheless, it's a pretty simple game, pretty straightforward game. Imagine you're player 1 in this game. You're player 1 in this game. What do you think you'd do? What would you do if you were player 1? Let's have a show of hands, actually. So let's just see. Look at it a bit. All right, no abstentions. How many of you would choose up? Raise your hand for up. Raise your hands for up. No, somebody, but you keep your hand up. You're an SOM student. You keep your hand up. Oh, your math is wrong. Okay. You did accounting last year. No one's choosing up. No one's choosing up at all. Okay. How about middle? One person chose middle. How about down? Oh my goodness. Okay, there's a massive majority for down. All right. So let's think about this a second. What if you knew that player 2 was going to choose left? What would you choose if you just happened to know that player 2 was going to choose left? Everyone agree? Because 5 is bigger than 1 and 5 is bigger than 4. So up is, to use a technical term we'll define formally next time, up is the best response to left. Everyone agree with that? All right, so up, as I say, does best against left. And what does best against right? Middle does best against right. After all, 4 is bigger than 0 and 4 is bigger than 2. So middle does best against right. Okay, so here's an interesting thing. All of you chose down, but up does best against left and middle does best against right. Let's just push this a bit harder. Suppose that you work for somebody. Some of you are going to go out of Yale and be your own boss, but most of you are going to, like me, are going to end up working for somebody. And suppose this game came along in your line of work and you'd chosen up. And then your boss came to you and looks rather fiercely at you, so this is Rick Levin or somebody looking rather fiercely at me, and says, why did you choose up? Right? And what can I do? I can say, oh, I chose up because I thought the other guy was going to choose left. Right? I have a way of rationalizing choosing up. If I believe the other guy is going to choose left, I can rationalize choosing up. Is that right? So it might save me from getting fired, at least for now. Similarly, if I'd chosen middle, and President Levin comes along to me and say, why did you choose middle? I can say, okay, I chose middle because I believed that the other guy was going to choose right, and middle was the best thing for me to do against right. And once again, if I'm lucky, I won't get fired. Seems like I've managed to rationalize choosing middle. But down, all of you chose down. Pretty much all of you chose down. Down is going to be a little trickier. How am I going to rationalize choosing down? Can I rationalize choosing down? You all chose it. I'm your boss now. Why did you choose down? Somebody who hasn't said anything yet. Can I get the mics up and perhaps the person right in front of you? Stand up and shout.
It's the safer answer if you can't decide whether or not your opponent's going to choose left or right, because you don't have to worry about having a payoff of 0.
All right. So in some sense, it's safer. It avoids the 0, although, I mean, it's true it avoids the 0, but it also doesn't get the 5 and the 4. But I think the key part of your answer was, I might not know. I might not be sure whether my opponent is choosing left or right. For example, I might believe that it's equally likely that they choose left and right. Is that right? All right? So let's look at something. Let's look at my payoffs from choosing these 3 options, up, middle, and down, if I think it's equally likely that my opponent will choose left and right. Okay? So what we're going to look at is the expected payoff of up versus, let me call it a half-half. A half-half being being equally likely that my opponent chooses left and right. So what's my expected payoff from choosing up, where I believe the other person's going to choose left and right equally likely? It's what? It's a half times 5 plus a half times 0 for a total of 2.5. Is that right? All right. What about my expected payoff from choosing middle against a half-half? So in this case where I think it's equally likely that my opponent's going to choose left or right. All right. So in this case, my expected payoff is a half of 1 plus a half of 4 for a total of, again, 2.5. Right, everyone happy with that? Is my math correct so far? All right. And how about my expected payoff from choosing down versus a half? A half. This is going to equal a half of 4 plus a half of 2, which is a half of 6, so that's 3. Right? So it turns out that, as the gentleman out there said, if I thought it was equally likely that my opponent was going to choose left or right, then actually my best choice, my best response, is to choose down. Right? Not only is it a good compromise, not only is it safe, it's actually the best I can do. It maximizes my expected payoff. All right? All right? Now, we're not quite there yet. We know that up does best against left, we know that middle does best against right, and we know that down does best if I think it was equally likely that the person's going to choose left and right. But that's not the only beliefs I could have. For example, I could believe that it's twice as likely that the person's going to choose left as right. It could be that I think they're twice as likely to choose left as right. So equally likely was probabilities of half and half. What probabilities are associated with thinking it's twice as likely they're going to choose left than right? What probabilities are associated with that? 2/3, 1/3, right? If I thought there was 2/3 probability they'd choose left and 1/3 probability they'd choose right, then I think it's twice as likely they're going to choose left. And I could redo this calculation. And in principle, I could redo this calculation for every single possible probability you could think of. Right? But that would get very boring. So rather than do that, let's draw a picture. what I want to do is, I want to draw a picture here right, in which on the horizontal axis I'm going to put the probability of the other guy choosing right. Right? It's my belief that the other guy is going to choose right. Think of this as a belief. All right, and on the vertical axis, I'll put two vertical axes in just for the sake of things. On the vertical axis, I'll put my expected payoffs. My expected payoffs. All right, and let's start by considering my payoffs on this picture. Just to help myself a bit, let me put some points in here. So I've got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. You should probably do the same in your notes. You probably have lined paper. That makes this easier. Okay. Let's start by plotting my expected payoff from choosing the strategy up. So this isn't so hard. We know that if I choose up and there's probability 0 that the other guy is going to choose right. Right? That's the same as saying I choose up and the other guy chooses. Let's try again. Right? If there's probability 0 that the other guy chooses right, that's the same as saying that the other guy is going to choose left. Okay. So the probability 0 of the other guy choosing left is the same as the probability 0 that they're. Try again. Probability 0 of their choosing right is the same as saying they choose left. So that my payoff from up against that is given by the top box up there. I get 5. All right, so this is my payoff from choosing up against left. All right, and conversely, if there was probability 1 that the other guy is going to choose right and I choose up, then I get 0. So this point here corresponds to my payoff if I choose up and they choose right. And we already know that if I look at probability 1/2, which is here, that the payoff I get from choosing, the expected payoff I get from choosing up against a 1/2 is 2.5. All right, so here's a third point we can use. Okay. And what is this graph going to look like other than these 3 points? What's it going to look like other than these 3 points? It's going to be a straight line. Okay, it's going to be a straight line. Okay, so you can confirm that for yourself at home, but in fact, if I draw a straight line, this will actually be correct. So what is this? This is my expected payoff from choosing up against the probability of the other person choosing right. And what is it actually equal to, just to confirm the equation? It's 1 minus the probability that they choose right. In that case, I'll get a payoff of 5 plus the probability that they choose right, in which case I get a payoff of 0. So it doesn't really matter, but that's actually the equation of that line. All right. What about choosing middle? Well, once again, we can plot that point. So if the other person's choosing right with probability 0, that's the same as saying they're going to choose left. And if I chose middle against left, I get what? I get 1. I should use this pointer. I get 1. All right, so that's here. And if I knew they were choosing right for sure, that's probability 1 they're choosing right. And if I choose middle, I get 4. That's here. And we've already agreed that if I think it's equally likely they're going to choose right and left, if there's probably 1/2 of them choosing right, I get 2.5 from choosing middle. So putting that all together, I know that they must go through here again, and once again, I get a straight line. I think I might have missed slightly, but that's more or less right. So what is this? This is the payoff to player 1 of choosing middle against left. This is the payoff to player 1 of choosing middle against right, and the line in between, this line here, is the expected payoff to player 1 of choosing middle as a function of the probability that other people choose right. And we could write down the equation. It's going to be 1 minus the probability they choose right times 1 plus the probability that they choose right times 4. And again, don't worry too much about the equation. We're not really going to do any math here. I'm just putting it in for completeness. All right, everyone following me so far? Okay. So let's put in now the third of these lines. I really should use a different color already. Let me switch colors. Let's put in the line that corresponds to choosing down. So that third line, not to belabor the point, is going to go through here, through 4, and through 2. Right, so this is the payoff from choosing down against left, and this is the payoff from choosing down against right. And I got those from looking at these payoffs here and here. And in between, once again, it's a straight line. So here's the straight line. And this line is, let's stick it out here, this line is the expected payoff to player 1 from choosing down, as it depends on the probability that the other person chooses right. And once again, we can write down the equation. It's 1 minus PR times 4 plus PR times 2. Right? And I claim that this picture really tells me everything I could possibly want to know when my boss comes along, when President Levin or Barry Nailbach, who's now walked in the back of the room, when my boss comes along and asks me, why did you do that? Right? Why did you do that? I can now say. So for example, let's put in these crossing points here. For example, what I can say is, if I think it's very likely, let's call this point x, if I think that the probability that the other person is going to choose right is less than x, then the highest payoff I can get corresponds to this line. That's the highest line, and that line corresponds to me choosing up. Right? So if I think the probability that they're going to choose right is less than x, then my best response is to choose up. Conversely, if I think it's more likely than this crossing point y, I think it's very likely they're going to choose right, it's more likely than y, the probability they're going to choose right is more than y, then the highest line of these three is this one, which corresponds to my choosing middle. So over here, my best response is to choose middle. All right, let's put that in. So over here, my best response is middle. And over here, my best response is up. And in between, it's going to turn out that the highest line, so if my belief that the person is going to choose right is more than x and less than y, then my highest expected payoff comes from that blue line, and in that case, my best response is down. I can rationalize all three of these decisions and hope that Barry won't fire me. And we can do more than that if we're being nerdy, but I'm not going to be this nerdy today. What we could actually do is we could solve out for the x and for the y. How would we go about, I mean, I don't want to do it because I'll probably get it wrong, but if I wanted to solve out for this x and the y, since this is a QR class, let's just talk about it a second, how would I do it? Somebody who's not a math major, tell me how I solve out for the x. I mean, maybe the math majors can't do it, actually, it's too simple. Somebody who is a math major, tell me how I'd solve out for the x and the y. We're going to mic on this person here.
Set the intersection points equal, the equations equal to each other, and solve.
Good. To solve out for x, x is when this blue line equals this red line, right? Right. So what we're going to do is take the equations for those two lines. So here's one of those equations, and here's the other one. Right. Set the p in those equations equal to x. I've got two equations and one unknown, so I've got one equation and one unknown. I've set these two things equal to each other. I've got one equation and one unknown, so I can solve out for x. I think I did that at home. If you do that at home, I think, but don't trust me, you'll find out that x is equal to a third. Let's just repeat. Again, I know I've got some math phobics in the audience, so let me just slow down a second. All I'm doing here is I'm saying, look at this equation of the pink line, look at this equation of the blue line. X is when they cross, i.e. they are equal to each other. Take these two equations, put an equal sign between them, replace this PR throughout with X. I'm going to have one equation and one unknown, and that even the math phobics in the audience did in high school. Is that right? All right. Now we're going to use, I'm going a bit slow here, but I'm going to use this method next time to introduce you to the most important the most important game we're going to see in the whole course. In fact, it's the most important game in the world. What is the most important game in the world? Don't go yet. What's the most important game in the world? We're going to use this idea of best response. We're going to think about it. We're going to learn from it in the most important game in the world. What is the most important game in the world? Football. Soccer, actually. Soccer is the most important game. All right? So we're going to show how this technique is going to help us shoot penalty shots in soccer. Before you go, that's Barry Nailbuff at the back. He has copies of the book. It's a great book. Go buy it from him.